آج شاید لیکچر کم اور کھانسی زیادہ آپ کو سننے کو ملے گی، لیکن کوئی بات نہیں. یہ سوال انفینٹی کیا ہے، اس کے دو علیحدہ مختلف پہلو ہیں. ایک جس کا تعلق ہمارے مادی کائنات کے ساتھ ہے، وہ اس لحاظ سے کہ انسان ہمیشہ سے یہ سوال کرتا آیا کہ کیا ہماری کائنات محدود ہے کہ لامحدود ہے. وقت ہمیشہ سے تھا اور ہمیشہ تک رہے گا. جو ستارے ہم دیکھتے ہیں آسمان میں، ان کی تعداد محدود ہے یا لامحدود ہے، انگنت ہے. یہ وہ سوالات ہیں جس کی طرف میں آخر کی طرف آؤں گا، اس لیکچر کے آخر. جو دوسرا پہلو ہے وہ میتھمیٹیکل ہے، جس کا تعلق خیال کی دنیا کے ساتھ ہے، مادی دنیا کے ساتھ نہیں. اور شاید یہ زیادہ پختہ ہے کیونکہ اس مسئلے کے اوپر بہت اعلیٰ ذہنوں نے سوچا ہے، اور آج میرا خیال ہے کہ ہم اس کو بہت حد تک سمجھ چکے ہیں. کائنات کے بارے میں اب بھی کچھ سوالات ہیں، وہاں بھی بہت کچھ ہم نے سیکھا ہے، اور وہ میں بعد میں آپ کو بتاتا چلوں گا. جب میں اسکول میں تھا تو ہمارے ایک ٹیچر تھے، وہ سری لنکا سے آئے ہوئے تھے، اور وہ کہتے تھے کہ infinity is a number, it is so big that if you start writing on the board, آپ یہاں سے یہاں تک لکھتے چلے جائیں 1 2 3 4 یہاں تک پہنچے، پھر واپس جائیں، آگے پیچھے ہوتے چلے جائیں، بورڈ بھر جائے گا، پھر ایک اور بورڈ لگا دیں. بہت بڑا نمبر ہے مگر وہ پھر بھی انفینٹی نہیں ہے. تو پھر آپ ایک اور بورڈ لگائیں اور ایک اور بورڈ لگائیں، اور اتنے بورڈ لگاتے چلے جائیں کہ آخر دنیا کا ایک پورا پھیرا ہوگا، اور وہ نمبر اتنا بڑا ہوگا کہ آپ تصور بھی نہیں کر سکتے، لیکن پھر بھی وہ انفینٹی نہیں ہے. اب دیکھیں یہ باتیں جو ہیں وہ لکھنا نا ذرا مشکل کام ہوتا ہے. مثال کے طور پر اگر آپ یہاں 100 لکھیں تو یہ ہو گیا 10 to the power 2. اگر اس کے بعد آپ ایسے کل 9 زیرو لکھیں تو یہ بن گیا 10 to the power 9. اچھا، اب اگر آپ یہ ایسے 100 زیروز لکھ لیں تو وہ ہو جائے گا 10 to the power 100. پھر اس کی تو کوئی انتہا نہیں، پھر آپ یہ کرتے چلے جائیں، لیکن پھر بھی وہ انفینٹی نہیں بنا. اچھا، اب میں آپ کے سامنے 4 عام غلطیاں سامنے رکھتا ہوں انفینٹی کی بابت. سو دس ول بی، پہلی غلطی یہ ہے، اور یہ صرف انفینٹی کے بارے میں نہیں ہے، پہلی غلطی یہ ہے کہ ہم سمجھتے ہیں، عام طور پر لوگ یہ سمجھتے ہیں کہ نمبرز کی اپنی کوئی حقیقت ہوتی ہے. سو دا فرسٹ، اس کو میں مٹا کر میں غلطیاں یک کے بعد دیگرے لکھتا چلا جاؤں گا. اچھا، سو four common misconceptions. پہلی بات یہ، numbers actually exist. آپ کہیں گے کہ یہ کیا بات ہے، پرویز ہڈبھائی نے یہ کیا بات کی کہ نمبرز डोंट एग्जिस्ट। देखिए, ये एक चौक है मेरे पास, उधर 4 और चौक पड़े हुए हैं, 1 जमा 1 जमा 1 जमा 1 जमा 1, कुल 5 बन गए। तो 5 तो है ना, 5 चौक हैं, 5 सेब हो सकते हैं, 7 कुछ और हो सकते हैं, कुर्सियां हो सकती हैं। तो इन सब का ऐसे लगता है कि वजूद तो है, आखिर हम अपनी नजरों से देख रहे हैं कि यहां पर 8 लोग इस पहली सफ में बैठे हैं। तो ये वजूद नहीं रखता? कैसे वजूद नहीं रखता? इसलिए कि ये तो मेरे सामने चीजें हैं, ये लोग मेरे सामने बैठे हैं वगैरह। 5 सेब या 5 चौक, ये बात तो अपनी जगह पे ठीक है, बशर्ते कि उसके साथ कोई ऑब्जेक्ट वाबस्ता हो, उसके साथ कोई ऑब्जेक्ट, कोई चीज, कोई शय मुंसलिक हो। लेकिन ये नंबर 5 क्या है, ये तो मैंने कभी नहीं देखा, आपने कभी नहीं देखा, ये तो महज हमारे दिमाग में एक ख्याल है। हाँ, 5 को आप कई तरह से लिख सकते हैं। 5 है 1 जमा 4, या 2 जमा 3, या 3 जमा 2। देखें, ऑर्डर मुख्तलिफ हो गया ना, 3 जमा 2 और 2 जमा 3। लेकिन जो रूल्स हैं जिसके तहत हम इन आदाद जमा करते हैं, वो वो रूल्स बड़े अच्छे डिफाइंड हैं। फिर नेगेटिव नंबर्स भी हैं। -2 वो अदद है जिसमें अगर आप 2 जमा करें तो उसका नतीजा 0 है। तो ये -2 डिफाइन हो गया। गोया कि हमने इन रूल्स के तहत नंबर की पहचान बनाई, उसे डिफाइन किया। अब आप कहेंगे ठीक है, बात तो ठीक है, बजाय ठीक है, लेकिन फिर भी मैं पूरी तरह से कन्विंस नहीं हूं कि नंबर्स का वजूद नहीं होता। चलिए, तो फिर मैं आपको एक और मिसाल देता हूं। कोई ऐसा अदद मुझे बताएं जिसको अगर मैं अपने आप से ज़र्ब दूं तो उसका नतीजा -1 है, -1। A number multiplied by itself gives you -1। ऐसा कोई है ही नहीं, मैंने तो कभी देखा ही नहीं। देखें, -1 इंटू -1 इज इक्वल टू +1, 1 इंटू 1 इज +1। और ये तो कोई फिट ही नहीं होती बात ना कि एक नंबर जब उसी नंबर को अगर दिया जाए तो उसका नतीजा -1 हो। लिहाजा ये 300 साल पहले की बात है कि इस अदद को बनाया गया, तसव्वुर किया गया, इसे इन्वेंट किया गया। इसे इमेजिनरी नंबर कहते हैं। और इमेजिनरी नंबर की बहुत गलत नाम था, क्योंकि ऐसे लगता है कि हाँ, वो दूसरे जो है 1 2 3 4 उनकी हकीकत है, लेकिन ये जिसको आयोटा कहते हैं उसकी हकीकत नहीं है, इमेजिनरी नंबर की हकीकत नहीं। मगर दोनों की उतनी ही बराबर की हकीकत है, वो एक मखसूस रूल से डिफाइन होता है। अब मैं आपको एक और मिसाल देता हूं। अब आम तौर पे आप ये समझते हैं, आपने ये देखा है कि 3 जमा 4, 3 ज़रब 4 बराबर 4 ज़रब 3 है, बोथ आर इक्वल टू 12। अच्छा, हम फिजिक्स में ऐसे नंबर्स इस्तेमाल करते हैं जिसके लिए ये बात ठीक नहीं है, दुरुस्त नहीं है। और वो एक मैथमेटिशियन के दिमाग की इजाद थी जिसका नाम था ग्रासमैन, और वो ग्रासमैन अलजेब्रास कहलाता है। और ये वो नंबर्स हैं जो बहुत काम के हैं। इमेजिनरी नंबर्स, देखिए, जब शुरू में ये इजाद हुए थे ना, तो लोगों ने कहा हाँ ठीक है, ये इसके साथ करना क्या, बना तो दिया आपने, लेकिन करना क्या ऐसे। वो इमेजिनरी नंबर्स इस कदर मुफीद साबित हुए कि आज आप तस्वुर ही नहीं कर सकते कि जो बिजली है, इस बिजली को हम समझ सकते ऑल्टरनेटिंग करंट्स खास तौर पे बगैर इमेजिनरी नंबर्स के। पूरी क्वांटम मैकेनिक्स का इन्हिसार कॉम्प्लेक्स नंबर्स के ऊपर है और ये सब ख्याली। तो ये सोच के नंबर्स की अपनी कोई हकीकत है, दिस इज रॉन्ग। एनी कॉमेंट? कोई? इज दिस acceptable to you?
Sir, I have a small request to make. We are Sri Lankan students.
Can you speak up a bit?
I have a small request.
Zohaib, can you turn on the mic, please? Yeah, okay.
Sir, we are Sri Lankan students, so I have a small request to make. Would it be possible to make the explanations in English?
Okay. So you want me to speak in English? All right. Has anyone got any objection to that? No. ठीक है, चलेगा? Okay, good. Please forgive me if I occasionally slip into Urdu, but that's okay. I'll do English most of the time. Okay. So this is wrong. This is a brilliant creation of the human mind, numbers. And we'll go on creating more numbers. Yes, sir.
अपने इमेजिनेशन को हमने ये इन्वेंट की है, तो हमें ये जो यूनिवर्स है ये इस कदर ऑर्डर्ड और मैथमेटिकल क्यों नजर आता है?
ये बड़ा गहरा सवाल है कि हमें कायनात में तरतीब क्यों दिखाई देती है? ओ, सवाल उर्दू में था ना, तो ठीक है, कोई बात नहीं। हाँ। So his question is, the universe seems very ordered to us. And if mathematics is just a creation of the human mind, why is it so useful in disentangling the order of the universe as we see it? And actually, this is a very profound question which was asked by Eugene P. Wigner, who got the Nobel Prize in physics and was one of the greatest physicists of his time. He wrote this article called The Unreasonable Effectiveness of Mathematics in Physics. It's unreasonable because you don't expect it. You don't expect these creations to describe nature, because after all, you're fantasizing. You're creating numbers where AB equals minus BA, the Grassmann numbers I was telling you about. So why could they be useful? Why are they useful? And the answer is, we don't really know. But it's this particular faculty of the human mind which is perhaps responsible. Anyway, there's a question we can maybe come back to at the end. Okay. Huh.
If you talked about numbers and you said that they actually don't exist, why our it means that our perception about reality is all wrong. Maybe we are just doing delusion because it's not a real thing which is happening. Isn't it like that?
No, our perception is what it is. We are all perceiving the same thing, and which is why we are able to talk to each other. What do you see as the color of this chalk? I see it as white too. Everybody here sees it as white. The fact that we are able to agree on that is telling us that there are some things that we agree on. We may not agree on whether Imran Khan should remain prime minister, but we can agree on the color of this as being white, right? So that is important from the set of common perceptions, we have drawn conclusions. From those conclusions, our imaginations have created things. Some of those creations have been useful, not all of them. There are things in mathematics, in pure mathematics especially, which have been created which are absolutely useless, so far as we know. Maybe someday they will come useful, maybe they will not. But the fact that we have created the mathematical apparatus, the mathematical equipment to understand reality, is what has enabled us to comprehend the universe. Okay, so that was one common misconception. Second, infinity is just a number, just a big number. And that is wrong as well. So let's see, let me talk about my old teacher again. And he said, you write this very, 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 very big number, and as big as you can write, with the boards going around the world 7 times. Well, that's infinity. But then if you add one number to that, that is also infinity. So now let's make rules based on that. There is a common depiction of infinity. The symbol for that is this, infinity. So this is now to be thought of as a very, very, very big number, right? As big as you can imagine and beyond. Now, if I add 1 to that, well, that's also a very, 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 very big number. And I'm also going to call it infinity. So infinity plus 1 is equal to infinity. ठीक है, इसमें कोई हर्ज नहीं. There is no harm in that. If I take infinity and multiply it by 2, I mean 2, I could put 7, I could put 21, I could put anything over here. That's also a very, 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 very big number. So many varies that it doesn't make any difference. So let me call that also infinity. It's fine. It's okay. No harm in that. What if I multiply infinity by infinity? Well, infinity is already pretty big, so I'll multiply it by another infinity, and since I've lost my powers of description, I'll just call it infinity anyway. So this is infinity. So this is fine. There's no harm in this. However, there are things that infinity cannot be used for. There are things that there are rules that infinity obeys which are different from that of ordinary numbers. So let me give you. So this is okay, okay, okay. Normally, if I take a number minus that same number, what do I get? 0. So I would expect infinity minus infinity to be 0, but no, 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 no. I would expect a number divided by itself to be 1. And so I would expect that infinity over infinity is equal to 1. And that too is no. Now you see, suppose I use these properties and these properties without the no, then look at the kind of contradictions that I am then faced with. So how this leads me into nonsense. Let me give you an example. Okay, so I have infinity. I'm ignoring the rules now. So I'm ignoring the no over here. Let's say that infinity minus infinity is equal to 0. Suppose that we accept it. Well, then infinity is also equal to infinity plus 1. We said that was fine. So this infinity over here is the same as infinity plus 1 minus infinity. And I haven't done anything to this side. But now I will use the first equation here, which says that infinity minus infinity is equal to 0. So let me write this a little different. You see, I can write a plus b is equal to b plus a. So I can write this as 1 plus infinity minus infinity equals 0. But you see, this here from here is equal to 0, and therefore I have 1 is equal to 0. It's nonsense. Okay. So you have to be very, very careful when you're dealing with infinity. You cannot treat it as an ordinary number. Let me give you one more example so that you're totally convinced of this. Let me write 0 in this one, in this form. 1 minus 1 plus 1 minus 1 plus 1 minus 1. And now I've run out of space, so I'm going to put dot, dot, dot. Right? Now I can write this in the following way. I can write this as 1 plus minus 1 plus 1. So this one I've written as it is. This minus 1 I've written over here because plus into minus is minus. The usual rules of arithmetic. And this plus 1 is here. Then the next one I will write as and so forth. And now because I've run out of space, dot, dot, dot. Theek? You're with me on this? Have I committed any illegality? No. You can have me punished if I commit a crime, an illegality, but I have not. You think I have? No. So what is this minus 1 plus 1? And this, and this, and there are an infinite number of zeros over here, there. And so now I'm adding up an infinite number of zeros there. And so I have 1 plus 0. Again, I've proved that 0 is equal to 1. What have I done wrong? Problem is that when you have an infinite sum, then you cannot then use the same rules as what you're used to earlier. So, to think that infinity is just a big number is wrong. Now, let me come to the third misconception. Any comment on this? White chalk. taking infinity away from infinity. Or let me put it in a nicer way. I thought I'd put it in a nicer way. So let me put it this way. All infinities are the same. This too is wrong. See, when you think of when you talk about infinity as being something very, 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 very big, then there is so much leeway in saying how big that in fact there are different infinities. And I'll give you an example where you can take away an infinite number of numbers from an infinite number of numbers and still end up with the same number of numbers. I'll repeat. I'll give you an example where you can take away an infinite number of numbers from an infinite number of numbers and yet end up with the same number of numbers. Yeah. I give you a very simple example of that. So let's look at 1, 2, 3, 4, 5, 6. Now I'm going to take away from here all these numbers, 2, 4, 6, 8, 10. And so I'm going to be left with, or easier, let me take away the 1, 3s, 5s, etc. So I'm going to be left with, so let me take away all the odd numbers. So what am I left with? I'm left with 2, 4, 6, 8, 9, 10, etc. Okay. So from here, there were an infinite number of numbers here. I took away an infinite number of numbers. Well, actually, if I divide this with 2, if I divide all of these with 2, then this becomes 1, and that's the same as the original set. We're only looking at the number of numbers. So how many numbers are there once I take away all the odd numbers? There are that many left, right? But these 2, if I divide that by 2, and this by 2, and this by 2, and this by 2, and this by 2, then I have 1, 2, 3, 4, 5. And so, in fact, I have the same number of numbers that I started with, even though I've taken away an infinite number of numbers. is, there's actually a word for that. It says that, so there's a word for that. It says that the word for that is cardinality. The size of this set and the size of this set is exactly the same. I mean, this is mind-boggling if you think about it, that you've taken away this infinite number of numbers and still are left with exactly the same thing. That's how peculiar infinity is. But now let me show you something even more peculiar. And when I encountered this while studying what is called real analysis, I didn't sleep that night. And this is the work that was done by a very famous mathematician by the name of Cantor. And I think this is just about 110 years ago or so. So what Cantor showed was that, I'll explain what a rational number is. He said there are as many rational numbers as there are natural numbers. So now I'll explain this point more. And this makes no sense. I mean, it's against common sense. So what is a rational number? Some integer divided by another integer. Not the same integer. It can be the same integer, but it could be different. So example of a rational number would be half, or it could be 5, 7, or it could be something very complicated over. These are all rational numbers. Okay, now it would seem that the number of rational numbers is much, 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 much greater than 1, 2, 3, 4, 5, 6, 7, 8, 9. Because look, at the top can be any number 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. At the bottom can be any number 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And so there are many, many more combinations that are possible. So how could the cardinality of the rationals be the same as that of the integers? Let me show you how Cantor suggested it. So you see here, earlier on what we saw was there was a correspondence between 2, 4, 6, 8, 10, 12 with 1, 2, 3, 4, 5, 6, 7. So there was this link. And that showed that there are as many numbers of this type, 2, 4, 6, 8, 10, 12, 14, as there are 1, 2, 3, 4, 5, 6. I'm going to use a similar reasoning here. So this is a rational number, 1 over 1. The simplest possible rational number. I'll exclude 0, but you can easily include 0. What about this? 1 over 2, 2 over 1. So, see, this is a rational number, and this is a rational number, but it's an integer. Let's go on. I'm making a pattern, and you will tell me when you see that pattern. So I mean there to be some distance between them. Then are you seeing the pattern? Then can someone tell me what will be the next block that I will write down? Yeah. So I put here 5. 2/4. 3/3. Okay, and one more, just one more. 1/6. 2/3/4. 4/3. And 5/2. And then 6/1. Nobody now has any difficulty in continuing this indefinitely. I mean, you can, keep doing this until tomorrow morning, and we'll run out of chalk, but that's okay. We'll buy some more. What's important over here? The important thing is that every rational number in this way will be covered. You remember this over here? I just picked this out of the sky. So will this number eventually come here? Yeah. It will. I don't know where exactly you have to, but it'll occur. What about another one? What about this? Will this number be there in this list eventually? Yes, because every rational number will be covered in writing down this. Okay, now, so what's the big deal? The big deal is the following. You see, suppose we are counting. So this is 1. This is the first one we've counted. This is the second one we've counted. Third one we've counted. Fourth one we've counted. No, not the fifth one, because it's been counted earlier. This is the fifth one we've counted. And so every rational number has been mapped into an integer. यार ये कोई बात है? This is mind blowing, you know. मुझे तो रात को नींद नहीं आई थी जब मैंने ये पहली बार देखा. इतने ज्यादा रैशनल नंबर और वो सब. So what have we learned? That the cardinality. So this, I'm going to erase this. So we've proved, among other things, that the cardinality of the rationals equals cardinality of integers. See, in a very peculiar way, there are as many rational numbers as there are integers. And now you've seen the proof of that. Okay, next. And this, अगर उससे नींद हराम हुई तो इससे तो पता नहीं क्या होगा. Now, unfortunately, I will not be able to prove this in a very, in the same way that I was able to prove this, because it takes you some effort. I think this could be taught in about 1 month, but okay. But if there's no time here, everybody can understand it. Everybody can learn it if they want. But it takes a little bit of time. What I'm going to tell you is something that you will have to take without proof. And that is the following. Imagine that this is the line from 0 to 1. So 0 is here, 1 is here. I take a number over here. This number is, so far we haven't talked about decimal numbers. But decimal numbers, all of these numbers can be converted into decimal numbers. So for example, you have 1 over square root, 1 over 3 is, when you write this in terms of decimals, this is 0. And how many 3's are there? An infinite number, okay. However, this is a rational number. If we have square root of 2, well, square root of 2, it turns out, cannot be written as a rational number. It is what is called an irrational number. There's a story behind this. So this is the mathematics school of Plato, Aflatun, great thinker. And you see, mathematics was something very mysterious in those days. And you didn't reveal its secrets to anyone. So there was only a small school of about, I don't know, 30, 40 students. And Plato was the great teacher. Plato believed in the perfection of the numbers, that the heavens move according to certain periods, intervals. Everything in the world can be quantified in terms of numbers. And numbers, perfection lies in numbers. Now, it was understood that there exist integers. Those integers, when divided by another integer, when that number is divided in this way, it leads to decimals, a decimal number. But it was assumed that all numbers could be written as rational numbers. So even 2 is 2 divided by 1. That's a rational number. But every number was assumed to be rational. And then one day, a student, he came silently to another student and he said, you know, I have discovered a proof that square root of 2 cannot be a rational number. And the other student said, shut up. मुंह बांध रखो, तुम्हारी खैर नहीं. So when the news reached Plato, or even before it reached Plato, I don't know, the story on this is a little confused, but they took that student who had discovered that square root of 2 cannot be written as P divided by Q. They said, let's go on a boating trip. And he was pushed overboard, missing. So then, of course, you can't keep these things hidden for very long. Square root of 2, which is 1.414, etc., cannot be written as P over Q, but take these, the rational numbers and the irrational numbers, and they give you what are called the real numbers. Now, here is something that I can't prove to you, but you will have to believe me because it will take too much time. If I have any two real numbers, between them is a third real number. And when I say any two, it doesn't matter how close they are. See, there's no integer between 5 and 6. This is 5, 6, 7. On that side, there's 4. But for a real number, if this is a real number and this is a real number, there is a third real number in between. Now, think about what that means. It means that you can make this number and this number as close as you want. Get closer and closer and closer and closer. But even then, there'll be a number in between. There'll be no empty space. So that is what is called a dense set in mathematics. All right, now here is the shocking thing. If I ask, how many numbers, how many real numbers are there between 0 and 1 as compared to between 0 and, let's say, 1.5, the answer is the same. There are as many numbers between 0 and 1 as there are between 0 and 1.5. And now just see what this means. It means that this is, if I ask, this is 0 and this is 0.00000000001, and I ask how many numbers are there between here and here, that's the same as the number of numbers here or here. It is so, you understand what I mean? How disturbing this is. And even more disturbing. Suppose I go to 2 dimensions. So this is the x-axis, this is the y-axis. And I make a small strip over here. I'll make it so small that you won't be able to, if I made it smaller, you would not be able to see it from the back. But imagine the smallest little segment that you can make and ask how many points there are. And the number of those points is equal to the total number of points in 2 dimensions. What about 2 dimensions, 3 dimensions, 4 dimensions? 4 dimensions, you just have to imagine there are more axes, nothing more. And so what we are used to in our daily lives, that the part is smaller than the whole, is wrong. Is wrong. And those are the things that infinity teaches us. And this is a long exploration from the Greeks down to Cantor. And there's a long mathematics and so much to explore over here. There's a word, it is called the aleph number. So I'm just throwing this word at you. The aleph number of the rational numbers is equal to the aleph number of the integers. But the aleph number of the real numbers is 1 degree greater than that of the integers. So it's a higher order of infinity. See, now we're talking of orders of infinity. All infinities are not the same. There is one infinity which is big enough. There is another which is of a different level altogether. That's the real numbers. Is there something bigger than that? The answer is yes. There is no limit to the order of infinities. So the aleph number, this was an invention of George Cantor as well. It tells you how to categorize sets in mathematics and orders of infinity. So very, very beautiful on that. And now I'm done with the mathematics. Now let me come to physics. Are there a finite number of stars in the sky? Yeah. Actually, I've forgotten how many there are, but they've counted them. And you can count them to some reasonable accuracy. That's actually not so hard because the universe is very uniform and it's very isotropic. Isotropic means that if you look at the universe over here with a telescope and you look over there with the same telescope and there and there and there, what you will see is approximately the same thing. Now, you have to look far enough for that. Don't look at the moon, don't look at the planets because they're in our neighborhood. We don't look at things so close, but look at the distant galaxies. That's where most of the universe is. So most of the universe then appears to us as uniform. And so from that, it's not hard. I mean, it is hard, but it has been done and it's quite reliably done. So the number of stars is indeed finite. What about the number of atoms in the universe? Is that finite? Well, if the number of stars is finite in the number of atoms, and fortunately I happen to remember that number is not a small number. Number of atoms in the universe. This was actually calculated by Sir Arthur Eddington in the 1940s. And he came up with an estimate which was, it was something like 0.9 times 10 to the power 80. And the modern estimate is something like 1.1 times 10 to the 80. Now 10 to the 80 is a big number, but it's not infinite, it's finite. And how you estimate this is very interesting, but we don't have time to go too much.
Is this number increasing or decreasing?
It's fixed now. It was fixed by the Big Bang. Yeah. Because now what they call baryon number is fixed. So then you can ask how many electrons are there? How many? That's the number of protons, roughly. Because most of the matter in this universe is what? Hydrogen. Hydrogen is a single proton. Then exactly equal to that is the number of electrons. Because you don't have a universe which has got a net charge to it. If it had a net charge, we'd know very well because every charge would be rushing off in that direction. So the number of electrons is equal to the number of protons. The net charge of the universe is 0. What about the number of photons? Well, it turns out, and I won't expect any of you to have to know this unless you have a deep interest in cosmology, but from what is our present knowledge of the Big Bang, there are 9 times as many photons as there are protons. So this is called the photon to baryon ratio. And so number of photons will be just 9 times this. Yes. Ji.
Number of stars are finite and the number of atoms are finite too. Does it mean the universe is finite too?
Okay, so I was just about to come to that and ask you that question. Certainly, the amount of mass in the universe is finite. The amount of energy in the universe is finite. But what does it mean to say that the universe is finite or not finite? Let's talk a little bit about that. In terms of the number of points that exist in space, of course it is infinite. We see that even in the smallest interval between this number and that number, the number of points is infinite. So the universe is certainly infinite in that regard. So that's not really that's not the real issue. The issue is, what is the size of the universe? Does it have a radius? And what lies beyond that radius? Because people always ask, where's the edge of the universe? Now, the fact is that there is a radius to that universe, of the observable universe, and that is roughly 13 billion light years. So if you were to draw what path a ray of light would travel, it would take roughly 13 billion years to go from one edge of the universe to the one part of the universe to the most distant one. But does that mean that the universe has got edges? The answer is no. It doesn't have a boundary. Think of it in the following way. We live on the earth, and suppose that you were not able to look up or down, not into the earth, not into the sky. You would be living on a two-dimensional surface. Does that have an edge to it? Of course, in the old days, they used to think if you go too far, you'll fall over the edge. But that we know is not true, because the earth is spherical, it's round. Good. In the very same sense, our universe does not have a boundary. It is an expanding sphere, but that sphere does not live in 5 dimensions. That sphere is in 4 dimensions. So it doesn't have, it does not have any boundary to it, and it is finite.
Can we say that this universe is extending to infinity?
Until a little while ago, we didn't know the answer to that question, because there are 3 possibilities. One possibility is that after the Big Bang, the size of the universe would increase, reach a maximum, and then gravity would start pulling it in. And then it would collapse, and then go back to what is called the Big Crunch. So that was a possibility, but it depends upon how much matter there is in the universe, and the observations were not good enough earlier on. The other possibility is that it expands, and then the expansion slows down, and essentially stops. And so the universe is neither expanding nor is it contracting. And this is actually what Einstein had assumed. He had assumed what is called the steady state universe. Well, it turns out that even that is not correct. What is now established, and there was the Nobel Prize in 2011, is that the universe is not only expanding, but the rate of expansion of the universe is increasing. And so it's an accelerating universe. How will it look like in the future? It'll just keep expanding. It'll get colder and colder and expand faster and faster, but that's the way things are.
Sir, what happened before Big Bang?
इसके लिए मुझे पानी पीना पड़ेगा. Everyone asks this. Why? What was there before the Big Bang? Well, I mean, it's a natural question to ask.
What about the energy density?
No. First, I have to ask. So, our physics fails at sufficiently high densities. If you take a movie of the expanding universe and run it backwards, then you'll see everything contracting down to one point. Now, when it gets small enough, when all the mass of the universe gets concentrated in a sufficiently small volume, at that point, our laws of physics break down. Then comes, so particle physics doesn't work anymore. The particles are so energetic and they're colliding with each other so hard that then the substructure of those particles becomes important. Then we get into the realm of what is called string theory. String theory then totally redefines our understanding of physics. And now the problem is that nobody understands string physics well enough to ask that kind of question. But I'll still tell you what some people think. And there's a good reason for thinking that. When we get down to densities which are that high, then space-time itself becomes a kind of foam, bubbling foam, and time loses meaning. What is time? Time is how we order events, right? A particle was here, then here, then here, then here. Time defined how it traveled. This happened, then that happened. First, second. So now imagine that there's this axis, the time axis. And now, when space-time starts getting distorted, and this starts, so far not so bad, but then what if it goes into loops? Then you don't know whether you're traveling forward in time or backward in time. And the whole issue of whether time is definable or not becomes then the answer to your question, what happened before the Big Bang? Maybe time ceases to exist. We don't know. Now we can only say we've observed the distant stars running away, we've observed this, we've observed that. On the basis of that, we make this and that prediction, and very good predictions. But we can't say we can answer that question today.
Why?
I told you why.
Probability and mathematics have that much power. Why we can't use them?
We don't have, they have a lot of power, but इस खोपड़ी में इतनी जान नहीं है. शायद किसी दिन उसका जवाब निकल आए, क्या पता. जी. मैंने कब कहा कि नथिंग है? कुछ भी. मैंने कहा हमें पता नहीं ना. हमें पता नहीं क्योंकि हमारी फिजिक्स तो देखिए ये भी बहुत बड़ी बात है कि हम एक माइक्रोसेकंड तक बता सकते हैं कि कायनात किस हालत में थी. एक माइक्रोसेकंड तक. उसके बाद जितना कुछ होता रहा है वो तमाम मराहिल हम न सिर्फ बता सकते हैं, लेकिन उसकी बिना पर हम पेशन गोइयां भी कर सकते हैं कि क्वार्क्स और ग्लूऑन्स थे, क्वार्क्स और ग्लूऑन्स फिर इकट्ठे हुए, उनसे न्यूट्रॉन प्रोटॉन बने, फिर उसके कुछ वक्त के बाद क्योंकि कायनात इतनी ठंडी हो गई तो उन्होंने प्रोटॉन्स ने इलेक्ट्रॉन्स को पकड़ा, उससे फिर हाइड्रोजन एटम बने वगैरह वगैरह। और अगर ये दुरुस्त है तो फिर आज कायनात में ऐसी ब्लैक बॉडी रेडिएशन मौजूद होगी। क्या हमने वो देखी है? यस, हमने देखी, वो पेशेंट गोई थी। इसीलिए हमें कुछ थोड़ी सी तसल्ली होती है कि ये इधर ऐसी फंटी नहीं मारी जा रही है। लेकिन जो सवाल आप कर रहे हैं ना कि क्या उससे पहले क्या था, कहते नहीं हमें वो क्या, हमें नहीं पता ना, हमें नहीं पता। जिस चीज का हमें नहीं पता, हमें नहीं पता। भाई इस बात पे आप शुक्र करें कि 10⁻⁻1 माइक्रोसेकंड से आगे तक की इतनी बातें आपको पता चली हैं। ठीक है, सवाल हमेशा करना चाहिए कि उससे पहले क्या था, लेकिन अब मैं कितनी बार ये कह चुका हूं कि नहीं पता, ना पता चलेगा। पता नहीं, मैं ये भी मुझे नहीं पता है कि हमें कब पता चलेगा। इस पे भी इन्हिसार है कि स्ट्रिंग थियरी में कितनी पेशरफ्त होती है। हाँ,
सर आई
या
What about the energy density? I read somewhere that the energy density of the universe is constant. So if it's expanding, so from where the extra energy is coming?
Are you talking of dark energy perhaps?
I don't remember, but
अच्छा,
it was
तो देखिए
constant.
एनर्जी डेंसिटी तो किस चीज की एनर्जी, एक तो मैटर की एनर्जी डेंसिटी हो सकती है, फोटॉन्स की एनर्जी डेंसिटी हो सकती है, लेकिन जिस सबब कायनात फैल रही है और इस तेजी से फैल रही है वो डार्क एनर्जी है। डार्क एनर्जी बुनियादी तौर पर क्वांटम मैकेनिक्स का एक नतीजा है। एग्जैक्टली कैसे है वो अब भी खोज लोग लगा रहे हैं। But yeah, energy density, you'll have to refine your question a little bit. The most important component of that today is dark energy. Huh.
सर आई हैव अ क्वेश्चन।
Yes.
एट द टाइम ऑफ बिग बैंग एनर्जी भी इन्फिनिट थी और डेंसिटी भी इन्फिनिट है, टेम्परेचर भी इन्फिनिट है। क्या हम इमेजिन या विजुअलाइज कर सकते हैं कि उस वक्त कायनात की ज्योमेट्री किस किस्म की थी?
देखें, the energy was not infinite. The density was very, very high, but we do not talk about infinities that loosely. We always take limiting procedures. So imagine that you are running your video backwards and you're running it back and back and back to 1 microsecond. At 1 microsecond, your video player starts to give up. It's because those conditions are very, very severe. Temperature is rising, the density is rising, your laws of physics are failing. So it's not that anything has actually become infinite. It's like this. Okay, you're asking me this kind of question. What is the value of 1 over x at x equal to 0? I don't have an answer to that question. It is, you have to let x approach 0. X can become smaller and smaller. 1 over x will become larger and larger. And so when we talk about the instant of the Big Bang, there is a singularity there. That x or that t or whatever is 0. And at that point, there's nothing that makes sense. You have to approach it. But even while you're approaching it, you know that your laws are failing. Yeah.
Is there something like the opposite of infinity? Does something like that exist?
Sure. So if I Infinity is a very big number, right? And that's 0. If I divide 1 by a very big number, that's 0.
So is that the opposite of infinity? The opposite of infinity is that that exists in mathematics?
I don't know what opposite means, but yeah, if infinity is big, 0 is small. Yeah.
When the universe is expanding, how come the radius is constant?
It's not. It's increasing.
Radius is increasing.
Yes, yes, yes.
You said a mathematical value that you radius.
That radius is increasing.
Okay, that's
And in fact, not only increasing, but the rate of increase is also increasing. It's an accelerating universe.
so we can't quantify that radius.
We can. Yeah, we
We
can.
know the exact rate of expansion.
Exact means, in this case, with reasonable accuracy. But nothing in measurement is ever exact. I mean, I don't know what is the exact height of this room. It's probably not even definable. If you were to ask me what is the exact height of this room, I don't think there's an answer that can even in principle be given. Yeah. I think there was a question here. Acha ji. हाँ. क्या फिर से अगर मैं 12 divided by 6
ये हमें 2 दे देगा
बिल्कुल
सर अगर मैं 2 को 6 से मल्टीप्लाई कर दूं तो मुझे वापस 12 मिल जाए
बिल्कुल सही
लेकिन 1 बाय इंफिनिटी को अगर 0 लिख रहे हैं तो हमें वापस 1 दे सकते हैं
तो ये आपका सवाल है नहीं इसलिए कि कुछ चीजें मना हैं जैसा कि आप इन्फिनिटी से इन्फिनिटी तफरीक नहीं कर सकते आप इन्फिनिटी को इन्फिनिटी से तकसीम नहीं कर सकते आप 0 और इन्फिनिटी को ज़रब नहीं दे सकते तो उस लिहाज से ये मना है हाँ मगर देखिए शुरू ही में मैंने आपसे ये कहा ना कि कुछ कवायद हैं कुछ ज़ाब्ते हैं उनकी आप खिलाफ वर्जी नहीं कर सकते तो आप इन्फिनिटी में से इन्फिनिटी नहीं निकाल सकते और ये नहीं कर सकते
Is there any infinity between two consecutive infinities? Is this possible, decidable?
हालत इसके बाद एक ही और सवाल No, I think I've reached my end. If is there an infinity between two infinities? Well, infinity is not a point, so I don't know how to answer that question. But you could define infinity minus 3 as infinity. So if you come 3 units down, that's still infinity.
My question is, so we have the infinity of rational numbers and the infinity of real numbers. Is there an infinity between them?
No. Of the rational or the irrational numbers, the real numbers, infinity is far away to the right, let's say. It's all there. When we talk about the number of numbers being infinite, that's a different issue. But infinity is some place far, far, far away. That's how we should imagine it. And there was a question there, yes.
What is the universe expanding into? Like, what is beyond the known universe?
The universe is not expanding into anything. The universe is complete in itself. The radius of the universe is increasing, but there's nothing outside over there. So again, I come back to this. We're living on this earth. There is neither the sky nor is there anything beneath. For us, it's the universe, our universe is the earth, okay? Now, the earth could be expanding, It could be a giant balloon which is being stuffed with air. And so the radius of that would keep expanding and becoming bigger and bigger. However, that would not be expanding into something, it would be by itself.
So essentially, outside it's nothingness.
Absolutely, yes. There's nothing out there. The universe is complete. The universe is everything that's there. Okay, thank you very much. It was